Lesson 7.5, the Doppler effect. Have you ever listened to an ambulance drive by quickly with the lights and sirens going? What does it sound like? Like wee woo. It's a high pitch as you're coming, low pitch as you're leaving. Watching a race on TV, the car goes, Eeum. High pitch is coming, low pitch leaving. Called the Doppler effect after Christian Doppler, who first labeled it. Here, the truck and everybody are at rest still. So the siren makes a sound. Sound goes out all directions. And everybody hears the sound. Well, what if the fire truck is moving? The fire truck is moving. See, the fire truck was here and emitted a sound that went out to here. And then the fire truck was here and emitted the sound that went out to there. And then the fire truck was here and made a sound that went out to there. And now the fire truck's here and makes that sound. So the centers of the sound waves are moving. So in the front here, when the truck is moving towards you, you have a smaller wavelength. Smaller wavelength means it's going to sound higher pitch. As the truck moves away from you, it's a longer wavelength. Longer wavelength will mean a lower pitch. Alright, so let's come up with our formula. If we're moving towards an object, our perceived wavelength is the wavelength of the wave minus the velocity of the source times the time of the waves. So it's where they were plus how far or minus how far the wave moved. And that gives you where your second wave is. Alright, the observed frequency then is the speed of the wave over the perceived wavelength, because speed is frequency times wavelength. But our perceived wavelength was the regular wavelength minus the speed of sound times the period. Our wavelength is the speed of the wave over the frequency of the source. Again, speed is frequency times wavelength. And the period is 1 over the frequency. So we can put those in and factor out the frequency of the source, and we end up with that. And so observed frequency would be the source frequency times this little thing where we're looking at the difference of the speed of the wave and the speed of the source. If the observer is moving, it'd be like the truck moving. You're going to hit more of the condensations, more of the waves, than if you were standing still. And so you'd end up with this, where you have more of the waves. It's like it's kind of going faster. So in general, we combine the different formulas so that both the observer and the source can be moving. We end up with this. Notice we have some pluses and minuses. The O stands for observer, the S is source, and the W is the wave. So the observed frequency equals the source frequency times this little ratio. We're looking at the speed of the wave, the speed of the observer, and the speed of the source. The speeds are signless. They're speeds, not velocities. You're going to use the top sign when the object is moving towards the other object. So here, this one here would be when the observer is moving towards the source. This one would be when the source is moving towards the observer. The top sign when you're moving toward the other object. So let's say you're driving down a road at 20 meters per second when you approach a car going the other direction at 15 meters per second with a radio playing loudly. If you hear a certain note at 600 hertz, what is the original frequency? Assume the speed of sound is 343. Alright, so that's the speed of the wave. We hear 600 hertz, so that's the observed frequency. We're looking for the source frequency. The car with the radio playing, so this is the source, and we are the observer at 20. So FO equals FS times VW plus minus VO over VW minus plus Vs. All right, we observe 600 hertz, looking for the source. Speed of the wave is 343. Now, the observed car, our car is going 20 meters per second. Now, is it going toward the other car or away from it? So as we're approaching, so we're going toward, we're going to use the top sign. Speed of the wave is 343. The source is 15 meters per second. Now, is it going towards the observer or away? Well, it's approaching, so it's going towards, so we're going to use the top sign. Put that in our calculator. This becomes 1.1. So divide by 1.1, and you end up with 542 hertz for the frequency of the source. Remember, it's coming towards you, so it sounds higher pitched, higher frequency. A duck is flying overhead. Well, you stand still. As it moves away, you hear its quack at 190 hertz. Because you're a brilliant naturalist, you know that this type of duck quacks at 200 hertz. How fast is the duck flying? Well, 190 is what you hear. So that's the observed frequency. And the source should be 200. You are standing still. You hear the one that hears it. So the velocity of the observer is 0. And we're looking for the velocity of the source. We also need the velocity of the wave. Well, they didn't say anything. So if they don't tell you, the speed of sound in air is going to be 343. So you have FO equals FS, VW plus minus VO, VW minus plus Vs. All right. So we observe 190. Source should be 200. Speed of the wave is 343 or close to that. And the observer is not moving, so it doesn't matter if we do a plus or minus since we'll be adding or subtracting 0. Okay, the velocity of the source is what we're looking for. Now, it says as it moves away, the top sign is towards, so the bottom one would be away. We're looking for Vs. All right, so what shall we do to solve this? Maybe let's get the variable out of the bottom. So I'm going to multiply both sides by 343 plus Vs and distribute. And the 200 times the 343. Subtract. And divide. So this duck is flying 18.1 meters per second. An application of the Doppler effect is NEXRAD, which stands for the Next Generation Weather Radar. So this is weather radar. It sends out radio waves, and within the waves bounce off water droplets and storms. The radar receives the echoes, and then a computer checks and compares the frequencies between the echoes and the original signal. And from that, they can see the change in the frequency. And from that change in frequency, we can see how fast the rain is moving towards or away from the station. So if you have two regions next to each other, let's say that region, it's going that way. The next region is coming that way. Oh, that's a circle. So that's one way they can check to see if clouds are spinning, which would indicate a tornado. So that's how a computer can monitor the radar and warn you quickly ahead of time about pending tornadoes.